So we've previously introduced the idea of black holes. The term comes from this gravitational collapse. Neutron stars can't be more than 3 solar masses. Anytime though you get enough mass of any sort crammed into small enough volume, and again, we derive the Schwarzschild radius equations in an earlier lecture, and so anytime you push enough mass that it gets pulled inside the Schwarzschild radius, anytime you get pulled inside the Schwarzschild radius, then you get this ultimate gravitational collapse. Everything pushes down to a singularity, and the Schwarzschild radius defines the event horizon. And so inside the event horizon, as we talked about, space is stretched, time is spaced, time is stretched, space and time almost interchange in equations and behavior. All the weird stuff, non-causality becomes a thing. The laws of physics don't apply properly. But the good news is all these things, if they were to happen somewhere in the universe, you have this wave of non-existence going across the universe, and everything blows apart. The entire universe ceases to function. But that can't happen because it happens inside the event horizon. We call it the event horizon because you have to go going faster than the speed of light to get away from there. You cannot go faster than the speed of light. We derived that earlier. And so any of these weird waves of non-causality or non-existence are trapped inside the event horizon and inside this object. And so trying to describe this is not even light gets away, and like what's inside the event horizon doesn't behave like it's in the universe anymore. This is what led to the term black hole. John Wheeler was trying to describe this because at a conference of theoretical astrophysics, mathematicians and theorists were explaining how all this stuff works, and reporters weren't getting the mathematics, and the mathematics was way more involved here than we were doing in this class, and so no doubt they were not getting it. In fact, I mean, this pushes it for physics majors, and even PhD physics majors have a difficult time with some of this mathematics. And so this is very difficult stuff. And so he was trying to explain it in simple terms. He said it's like a big black hole in the universe. And so that's where the term black hole came from. But remember, near the black hole, near the singularity, that singularity does weird things to the laws of physics. And so causality doesn't work. The basic laws of physics no longer work at that point. So Roger Penrose comes along and he says, well, in that case, then what happens is that we can define something that we call the law of cosmic censorship. And that is, you can never have a naked singularity. A naked singularity be a singularity that's not hidden by an event horizon. If it's hidden by an event horizon, all the non-causality, the breakdown the laws of physics, the wave of non-existence and disruption of physics that allows the entire universe to cease functioning is trapped inside the event horizon. And so even though all this stuff may be happening by the singularity, singularities inside the event horizon, none of that stuff can make it out, and so the universe is saved. And so this is the law of cosmic censorship. Okay, so space is massively distorted near the black hole. So as you're going close to the black hole, all the effects we talked about before about the curvature of space around the sun are magnified here, exceedingly magnified. Well, it also means another interesting weird thing happens, and that is all the stretching of space, okay, happens. And so the stretching of space makes for all kind of other weird things. And so, but that only happens near the black hole. So if you have the sun, okay, and you're 1 AU from the sun, then it exerts a certain force on you. If you're 1,000,000 miles from the sun, it exerts a certain force on you, more so than 1 AU. If you are 1,000,000 miles from a 1 solar mass black hole, it does exactly the same thing. So the black hole doesn't just go around eating the universe. You know, the gravity doesn't become stronger, it becomes more concentrated. Now, if you were like 100 miles from the center of the sun, you'd be inside the sun. Okay, and so you'd have part of the sun pulling backwards on you, part of the sun pulling one way, so gravity would be less. You know, you'd actually experience less gravity there because you have some of the sun above you pulling upwards. But 100 miles from a black hole, it's all still one side of you pulling on you, and so gravity is getting more and more concentrated. So at that point, you're starting to see all these weird gravitational effects occur. So it's only when you're very, very close to the black hole you get these weird gravitational effects. So space is stretched near a black hole. That's what this diagram right here was trying to show you. So, but there's another thing it tries to show you. It's like, you know, if you want to get to here, you don't just go that distance, you got to go around the curve. So to get further into the black hole, you got to go even further, even though that's not really that much farther distance than that first part. So let's look at this another way. So suppose you had a black hole and you're in orbit around the black hole. So you got the black hole right there. And so you're in orbit. Now the distance, suppose you measure the distance around your orbit. You know the distance around an orbit is 2 pi r. Okay, so if you measure the distance out here and it's 2 pi times 40 kilometers, that means you're 40 kilometers from the black hole. Now, if you fly 10 kilometers towards the black hole and you go around, the distance around is going to be 2 pi times 30 kilometers because you're 30 kilometers. 40 minus 10 is 30. So then you fly another 10 kilometers towards it and you go around. And so you would think 2 pi times, 30 minus 10 is 20 kilometers. So, fine. Then you go another 10 kilometers closer, and then you go around. Well, 20 minus 10 is 10, but you would come up with 2 pi times 11 kilometers. So wait a minute. That means that 20 minus 10 is 11. So that sounds weird. So you're 11 kilometers from the black hole, so you fly another 10 kilometers towards it. That's getting dangerously close to it, but when you go around, you realize the distance around is like 2 pi times 5 kilometers. Oh, wait. 11 minus 10 is 5. So now you go another 10 kilometers. So you're 5 kilometers from the black hole, so you fly 10 kilometers towards it, and now you go around, and it's 2 pi times 4 kilometers. And you say, wait, how did that work? I mean, you were 5 away, you flew 10 towards it, you're still now 4 away. So you're 4 away, so you fly another 10 kilometers towards it, and it's 2 pi times 3.5 kilometers. And then you're 3.5 kilometers away, you fly another 10 kilometers towards it, and now it's like 2 pi times maybe 3.25 kilometers. So you only got to, so what's happening? Well, what's happening is space is stretching as you go towards the black hole. And the farther you go, the more stretched it is. And so the more and more you go towards the black hole, the more and more space in the direction the black hole is being stretched. So that means it's an unbelievable distance you have to go to get to the black hole. And that's what that diagram is trying to show you. Astrophysicist Kip Thorne talks about if you were to actually fall into a black hole, space is being stretched so much that one end of the spacecraft we stretch vastly more than the other end of the spacecraft, and he calls this process spaghettification because you're stretched out like a piece of spaghetti. Okay. And really, you wouldn't just be spaghettified because they get closer and closer and closer. The part closer to the black hole wants to orbit faster, and you'd be ripped apart into just individual atoms going around the black hole. You can't really see a black hole because the black hole bends light. So imagine, a black hole the size of the little green circle in front of this guy's face. What would that look like? Well, classically you might think just a little dark spot there. Well, really it's bending light around it. So if you look at that spot, you wouldn't see the light. You'd see the light from behind your head looking at you. So it would distort the view. So light's bent around a black hole. John Wheeler also introduced the idea that you can describe a black hole by just 3 numbers: mass, angular momentum, and charge. So it has a certain mass that determines the size of it. Angular momentum, everything in the universe has some angular momentum, and so you don't lose angular momentum when you shrink down to a black hole. So the black hole is some angular momentum and then electric charge. And so these properties define your basic black hole. We'll talk more about that coming up, because it turns out the type of black hole we're talking about is what we call a Schwarzschild black hole. It's one that has no angular momentum. If you have angular momentum, you have to have a little bit different mathematics to describe it. That mathematics was worked out by Roy Kerr, and Roy Kerr worked out the mathematics, and so we call that a Kerr black hole. And so that is the mathematics that describes the space around a rotating black hole, and that will be our very next topic.